Good morning, good afternoon, everyone. A warm welcome to all our attendees today from across the globe. We want to thank you so much for joining us for this webinar today on Big Data Architectures, Beyond the Elephant Ride. My name's Lisa Glenn, your host and presenter for today's session. Now, joining me today as the expert speaker is Saurabh Dutta from the Impetus Labs. Saurabh is the key member of our Big Data team and has established a great expertise in this domain and has some great insights to share with you later on. So in this 40-minute session today, we're going to look beyond Hadoop and really explore some of those new and emerging technologies which would effectively address some of Hadoop's limitations. So let's dive in and take a look at what today's session has in store for us. So today, we're going to start with just a quick introduction of Hadoop, where it can be used, and also some of its main challenges and bottlenecks. We're then going to discuss some of the problems where we actually advise not to use Hadoop, and we're going to suggest some other more effective options that could be considered. Then finally, we're going to have a look at what really should be your ideal strategy around big data. Now, before we begin the presentation, I just want to quickly share here that nowhere in this presentation are lying that Hadoop is losing its charm. We just want to talk about a few of those alternatives out there which do work where Hadoop really is not very effective. So, having said that, let's go ahead and begin, and we're going to go back to the very basics, and we're going to ask the question, what is Hadoop? So I just want to give you a quick overview of Hadoop and where it can be used. So Hadoop is a large-scale batch data processing system that is comprised of primarily two parts. The first is HDFS, or Hadoop Distributed File System, which is used for storage. And then there's MapReduce, which is a parallel programming model and framework that is primarily used for processing big data. So that brings us to the next question, which is, what exactly is big data? Well, there's no really defined boundaries of what big data is because it really differs on a case-by-case basis. But for us, big data is any amount of data that you just can't store and process using the conventional methods. This ranges from gigabytes to petabytes on to exabytes. Hadoop is extensively used by the technology giants out there like Google, Yahoo, and Facebook, and now adding to its already immense power that it has are all of its sub-projects that are developed around it. So these sub-projects, such as Mahout, Sqoop, Flume, Pig, and others that you can see now on your screen, are really an integral part of the entire Hadoop project. So now let's take a look at some of those common places where Hadoop is used. And I just want to run down a few real quickly here. So the first place is risk analysis. Hadoop is very effective in use cases such as intrusion detection and also credit scoring. The next use case of Hadoop can be for recommendations. And I'm sure you've seen that a lot of websites, for example, Netflix and Amazon, they recommend products that are based on your interests. And here Hadoop can really be effective. Now, additionally, you can also use Hadoop for sentiment analysis, which is another really interesting area that is catching up. Again, as you know, a lot of sentiment gets generated on various blogs or forums, and especially social networking sites. Now, more often than not, this sentiment, it goes uncaptured due to that unstructured format of the data. And again, Hadoop can be a very effective tool in detecting these sentiments. Now, another important area where Hadoop can be used is for targeted ads. These ads are very important for advertisers as well as customers out there today. Advertisers have no desire to display their ads to the wrong set of people who really are just not interested in their offerings. So Hadoop plays a crucial role in displaying those targeted ads and really maximizing ROI on the ad's expenditure. Now also, machine learning is another really interesting area where Hadoop is being leveraged these days. Now, a very complex but very important task, such as identifying spam vis-a-vis other important emails, is an ideal case of machine learning and can be effectively addressed via Hadoop. Now, in addition to all the use cases I just discussed, there's also a lot of other areas where Hadoop can also be a perfect fit. So Hadoop has gone a very long data, but big data still spans across some important issues that Hadoop alone does not address. And so now we're going to dive in and take a look at some of the limitations of Hadoop. Like I mentioned, we know that Hadoop is a great product. With version 2.0 alpha, it's really overcome a lot of issues present in their earlier versions. But there's still a few more areas where we'd like to see Hadoop make some progress. For example, we're still a little away from foolproof Hadoop security. And what I'm talking about here is authentication and authorization, which are both big challenges in Hadoop. It's really very difficult to determine whether the users are actually who they claim to be. And since MapReduce runs applications as the user, it is paramount that we are able to authenticate them. Now, another limitation that Hadoop still has a lot of language and OS-related restrictions. It only runs Linux and is tightly coupled with Java. Oh, and writing Hadoop jobs is also a little messy as well. So the challenge here is that data analysts and data scientists, they find it hard to interact directly with Hadoop. You really have to be comfortable with programming to run these jobs. Now, thankfully, there are interfaces like Hive and Pig that give us a layer of abstraction, but you still have to get your hands dirty in all of it. So let's move on to the next limitation, which is batch processing. So we know that Hadoop is still strictly a batch processing system. So while Hadoop helps cut down the turnaround time of the classic ETL process, unfortunately, we're still far from real-time production deployments. And again, despite being a great solution for batch processing applications, it's still going to be really interesting to see when we're able to do real-time analytics on Hadoop. So Hadoop is a powerful tool, but as I just mentioned, it is not a silver bullet. You really need to be aware of other upcoming technologies that maybe address more effectively big data challenges in other scenarios. So let's go ahead and take a look at some of those. So for example, there are some promising flavors from Cloudera, Hortonworks, EMC, Greenplum, and MapR. So each of these flavors has their own strengths and also their own shortcomings. So you really have to carefully choose the best one as per your requirements. Now, let me give you just a glimpse of the kind of additional benefits that you can get by taking an example of MapR. Hadoop usually works on the write once principle, but in MapR distribution, the user gets a lot of flexibility to modify, change, and just overwrite the files. Similar to a general file system, users can browse files and then automatically open files with associated programs just via mouse clicks or by dragging and dropping files in and out of the cluster. So as far as convenience is concerned, this is a huge leap forward. Now also, MapR has a really interesting feature of being able to prioritize smaller MapReduce jobs. So again, in the traditional Hadoop distribution, all jobs are considered to be of the same priority. But with MapR's Express Lane feature, those small jobs are identified and are executed even when the cluster is loaded with other heavier jobs. Now, another advantage that I want to point out is that you can let go of the batch mode. In most of the Hadoop distributions, the data needs to be loaded first in a batch mode, and then you can perform analytics over this data. So the data typically resides on a network or direct or network attached storage. But if you do use MapR, remote clients, typically your applications, can mount this cluster and start writing directly into the cluster. So now, all of this data is available to your analytical workflows. So basically, these are just some of the kind of additional benefits that you can expect with various Hadoop alternatives. So now let's consider another common problem area where Hadoop doesn't go very well, which are the transactional systems. Now, by transactional systems, we mean e-commerce websites or, for example, carrying out a transaction using an ATM. These are the kind of solutions that require a quick response time to the user. A lot of big websites out there are just unable to handle these problems using traditional systems, and that's where the alternative solutions can really come into the picture and add real value to you. So here, I'd like to take up NewSQL. So NewSQL is a term. It's used for various new scalable and high-performance SQL databases. And what you need to keep in mind is that the new is not about SQL. It's actually about the new vendors that are offering horizontal scalability in their products. Now, there's various approaches taken by different vendors to achieve this horizontal scalability. And I'd just like to explain this to you with an example of VoltDB to show you how they achieve scalability. Okay, so VoltDB is an in-memory database based on share-nothing architecture, and its high availability is due to the multiple copies of each partition. So instead of just arbitrary SQL queries, you actually interact with VoltDB using the stored procedures, which are designed to perform extremely fast even if you're working on low-end machines. So what happens is that you specify how you want the data to be partitioned or replicated on a per-table basis. There are then further subsets of data created in the database. And as you can see on the image on your screen right now, you'll notice different tables, A, B, C, and D. In VoltDB, we decided that A, B, and C will be horizontally partitioned across multiple servers in the cluster. So as you can see, there is one portion of table A on each of the different servers, X, Y, and Z, and then similarly, tables B and C are also split. These tables are partitioned in VoltDB based on a primary key that your developer or designer would specify. Now, when you choose partitioning keys that match the way the data is accessed by the stored procedures, it optimizes execution at runtime. So, as you can see, table D in this image is replicated on all the machines of the cluster instead of being partitioned as table A, B, and C. Now, we did this to further optimize the performance because VoltDB allows certain database tables to be replicated to all partitions of the cluster. So say for small tables that are largely read-only, this actually allows stored procedures to create joins between the table and another larger table while still remaining a single-sided transaction. So now I want to move on and discuss another use case, which is actually about real-time computation. Now, not surprisingly, we know that decision makers always want speedy access to information and then, of course, to have it act fast. This is now actually possible thanks to a lot of great solutions out there providing real-time computations. Some examples include continuous computation, for example, like trending topics on Twitter and Google, or maybe stream processing that can perform analytics over live streams, say Twitter Firehose. So in these scenarios, you're not going to be able to use Hadoop, but instead, you're going to need to explore other options like maybe Storm, Esper, S4, Cloud Scale, and so on. In fact, Storm is actually sometimes referred to as the Hadoop of the real-time world. Now, before we go ahead and see another architecture example, it's really important to understand what Storm is. Sarb, can you go ahead and explain this to us a little bit better?
Sure, Lisa. The technologies you mentioned like Storm, Esper, S4, Cloud Scale, all of these technologies are really powerful. Here I would like to take the example of Storm. So there are 4 terms that you should be familiar with. So in Storm we have spouts, bolts, streams and topologies. So a spout is a source of streams in a topology. So this is what injects the data into your system. A spout can connect to an AMQP server like RabbitMQ, or to a Twitter streaming API, or a Redis PubSub. Then we have streams. A stream is an unbound sequence of tuples, and tuples can belong to a certain named class. So a stream is like a series of instances of a certain named tuple class. What are bolts? Bolts are processing units. They can consume one or more input and produce 0 or more outputs. Bolts can do anything from filtering, functions, aggregations, joins, talking to databases, things like that. And finally, we have topologies. So topologies contain the real-time application logic. These topologies are graphs of spouts and bolts that are connected with a stream grouping. So while Hadoop runs finite MapReduce jobs that are concluded eventually, Storm topology enables processing of messages forever, or until it is killed. Now let us explore this architecture with help of an example. Here is the use case. Assume that you have a high traffic website which gets hit by different parts of the world. You can view where your website is being accessed in real time. So for visualization, this data might be represented in form of pins dropped on a map. So as a website is being accessed from a particular location, a pin is being dropped to the map corresponding to that location. In this example, we'll take Redis as a PubSub spout. The spout can read a continuous log line and pass it to corresponding bolts for processing. Here we have this bolt, which is a stateless parser to extract the IP address information. will then pass the IP address location to the next bolt, which is a geolocator. Based on the IP address, this geolocator bolt will have the processing logic to extract the exact location of that IP address. And finally, the geolocations will be fed to a pusher, which will then send this data to the client's browser via a remote call, maybe to a WebSocket server. There could be a slight variation to this problem where you might just want to drop one pin for aggregated request from a location. In that case, you can also group all the locations before sending it to the pusher bolt. That's how you take the live data and process it very effectively using Storm to see the result in runtime. So that's how a real-time architecture works in this case. I hope this explains it.
Thanks, Saurabh. Yes, it does. That was great. Let's now move forward and take another use case of storing graph-like data structures efficiently. So the best way to store this type of data is actually using a graph database. And let's go ahead and talk about that a little bit. Unlike any other databases that store data in rows and columns, or maybe even key value pairs, the graph database emphasizes on nodes and edges. So nodes and relationships, which are also called edges, are native to a graph database, and they ensure that the graph is consistent. So in certain scenarios where graph database is actually not being used, we can only form an implicit graph data structure, but a graph database actually represents a graph. Now, there's a lot of use cases where graph databases are a natural fit. For example, in social networks, it's just easier to use a graph data structure to represent all those friend relations and do transversals and queries, perhaps like get me all the friends of my friend's friends. So again, in this scenario, we recommend using technologies like Giraffe and Pregel. Now, let's go ahead and take an example which I'm sure all of us have come across in LinkedIn to illustrate graph database use. So let's assume that we are looking for degrees of separation between, say, node 1 and node 6. When looking for paths from node 1 to node 6 using undirected relationships, all nodes except node 7 will be a part of at least one path as shown in the diagram right now on your screen. So this algorithm will finish in just 2 steps. First of all, we'd like to get all possible paths from node 1 to node 6 and then find out the shortest one by sorting all the resulting lengths. Now, if for some reason we use directed relationships, the result will be found among the nodes that are colored gray in this graph that you're looking at. So using graph databases in this type of scenario really eliminates a lot of complications you may encounter. A relational model is based on the assumption that database records are the primary consideration, while then the relationships then between those records come secondary. Now, on the other hand, graph databases assume that the relationships are just as important as the records. Now, this is an important distinction, and it has numerous consequences, really for ease of use as well as for performance. A table-based system makes a really good fit for any static and simple data structures, while a graph-based system fits more complex and dynamic data better. So it really depends on the data. So now I just want to move on and talk a little bit about another area where Hadoop, again, might not be very effective. So there's a lot of instances where we need fast, key-based access. And in these cases where you need that fast access, going for a NoSQL solution makes the most sense. NoSQL is designed to solve a host of big data problems. And NoSQL database management systems are really most useful when you're working with a huge quantity of data and in scenarios where that data's nature doesn't require a relational model for the data structure. Now, some examples include maybe showing the latest list of items added on your homepage, or maybe using NoSQL databases for building extremely fast caching mechanisms. NoSQL database systems are highly optimized and for that retrieve and append operations, and they often offer little functionality beyond that basic record storage, for example, key value stores. Now, most of the NoSQL systems employ a distributed architecture with that data held in a redundant manner on several different servers, often using a distributed hash table. So in this way, the system can readily scale out by adding more servers, and so a possible failure of one server can actually be tolerated. And again, I just want to ask Saurabh to explain this a little bit further. Saurabh?
Sure, Lisa. Let me again take help of an example to explain this. Providing listings such as latest items added by our users or latest comments is a very common problem of web applications these days, and it is also often a scalability problem. In the traditional relational approach, feeds displayed to a user needs to be generated at runtime, that is, at the time when you receive the request from the client. This involves joins and sorts across multiple tables, and this might really hit the performance. We believe that this and similar problems can be fixed using a Redis pattern. In this example, we want to show the latest 20 comments posted by our users. Near the latest comments box, we also have a link, let's say show all. This could link to a page where it is possible to show more than the latest 20 comments, and there is also pagination so that we can see the whole comments timeline. We also assume that every comment is stored in our database and has a unique incremental ID field. We can make both the homepage comment section and the comments timeline with pagination fast using a simple Redis pattern. How? Let's have a look. We need to do a couple of things before we can actually retrieve the list fast. Every time a new comment is added, we add its ID to the Redis list, ID underscore list in this case. We also trim the list to a given length so that the Redis list will just hold the latest items. In this case, we are assuming the list to hold the latest 5,000 items. Now, every time we need to get a range of items from our latest comments, we just call the getLatestComments function shown in the pseudocode. What we are doing here is simple. In Redis, we are taking a live cache always updated with the latest 5,000 IDs. When the system is initiated the first time, these IDs can be even zero as the list did not exist earlier. And thereby the new function which retrieves the IDs of the latest comments will take Redis assistance. If our start or count parameters are out of range, we'll have an option to fall back to the database. We get a performance boost because we would not need to refresh the cache with this system, and the SQL database will be only pinged if the user is paginating far intervals. Since Redis is not working as a traditional cache, there are no cache refreshes, and the information in Redis instance is always coherent. The NoSQL stores are really important these days, and when designing large-scale systems, one should definitely use the power of these systems.
Thanks, Saurabh. That was a great explanation. Now, again, like we shared, there are a plethora of options available that address some of Hadoop's limitations. And what I've discussed in this presentation is really just a subset of those options. I just want to give you now a quick recap of some of those alternatives that we've discussed before we go on and get into our recommendations to build a successful big data strategy. So again, just to recap, if you are planning to invest in Hadoop or maybe have already invested, the options that you should watch out for are MapR and Hadapt. There's also some Hadoop flavors from Cloudera, EMC Greenplum, IBM, and Hortonworks from Yahoo, which are hardened for enterprise usage. In fact, some of these options are even free and also completely compatible with the Apache Hadoop ecosystem. Some of the other promising alternatives to Hadoop, are HPCC and Disco. Now, interestingly, LexisNexis open-sourced their platform, HPCC, which was being labeled as a Hadoop killer by some in the community. And it was being claimed that it will outperform Hadoop in both data volumes and response time. So HPCC systems directly take on Hadoop, which is really not wrong as far as the functionality is concerned, but architecturally, you really just can't compare them. Hadoop is based on the MapReduce paradigm, whereas HPCC is not. Now, Disco is another distributed computing framework based on the MapReduce paradigm. Disco is open source, developed by Nokia Research Center to solve real problems in handling massive amounts of data. The Disco core is written in Erlang, a functional language that's designed for building robust, fault-tolerant, and distributed applications. If you have any complex business queries or maybe online transaction processing, where there's a lot of emphasis on the response time, maybe try evaluating the new gen SQL like VoltDB, ClusterX, Hadapt, etc. Now, if you're looking to build a real-time solution, options like Storm, CloudScale, S4, and Esper can play a crucial role for you. Storm, when used with Esper, is a great way to help you build a very scalable real-time solution. Now, apart from all these technologies that I just listed, there are some other sets of technologies that are going to be hot in the future, and you definitely want to keep a tab on those. We actually recommend to opt for OpenMPI and BSP if you need a high-performance supercomputing for modeling and simulation-related problems. So the next three technology areas that I'm going to talk about involve serious interest of Google, as well as they're using themselves, and they themselves are actually using it. So Google has a project called Preagle, which they've developed for building highly efficient, very large-scale graph computing needs. So if you have requirements of low latency querying on extremely large sets of data, there's a project called Dremel from Google, again, that might help. So Google itself has moved on beyond Hadoop, and their next generation of infrastructure is based on Percolator or caffeine projects. Now, this doesn't change the search results, but actually improves the indexing mechanism. In fact, Google also published a paper on Percolator, one of the back-end systems similar to caffeine. For the end user, this change allows reducing the delay between that when a page is found and when it is made available in the Google search. The previous system was based on MapReduce and used a batch approach, while this new Percolator-based system they created is much more real-time. So now, let's move on to the next part of our presentation today, and we're going to talk about your big data strategy. So here's the big question. What should a big data strategy look like, and what's beyond just Hadoop? I'd like to share some recommendations that you really should consider while building your big data strategy. But before we do that, I just want to know where you are currently with your big data strategy. We're actually going to do a poll right now that you can see running on your screen on the right, and your options are planning a big data initiative, already established a big data strategy, or facing problems with your current strategy, and finally, seeking help for developing a strategy. You actually have 30 seconds to respond now, and you can choose multiple options if you like. Okay, it looks like we've got the poll results, and it looks like most of you opted for that first choice, which was planning a big data initiative. So many of you are in that planning stage of big data strategy, and we're really sure that these recommendations coming up are really going to help you. So as you know, we've been talking a lot about real time, so you need to maybe shift your thinking in that direction as well. We recommend scaling up your thinking beyond Hadoop toward real time. So like the current NoSQL world, there would be a no Hadoop world very soon. Now again, no Hadoop does not mean not Hadoop. Rather, it really indicates toward not only Hadoop. You know, there's so many technologies that can help you in building efficient systems, and the trick is you just need to identify the right one as per your use case. Now, there was so much talk during the beginning of the big data era about the limitations of SQL and stories of SQL not performing as demanded by the new systems. But the real truth is that we're moving back to the SQL world. It's really a very sound technology and really works well in handling large sets of structured data. Hadoop and SQL aren't competitors, but they actually really complement each other very well. Now, integrations and visualizations is another key strategy for you. Visualizations and dashboards have the ability to capture the picture on big data, and especially, again, in real time. We also want to advise you to maybe think about taking your big data closer to your operation systems. Now, when you do this, your forecasting systems, SCMs, CRMs, can process your data in real time and let your operational systems use it without long waiting periods. Now, on your screen now, you can see our recommended strategy for handling large data mixes, real-time processing with that batch-oriented data processing. It's really a pipeline where you have both structured and unstructured data coming in. So in this strategy, there's a layer of connectors where you can actually connect to structured sources like databases, structured log files, maybe click streams, and then there are unstructured sources like videos, images, documents, etc. If you do wish to do real-time analytics over the data coming from all those various sources, one option is to divide that stream into two parallel paths. One path could go into the real-time engine, where then you can perform analytics on the latest data that's coming in. And on that other line, you could go into batch processing engine where you can then perform analytics on a larger set of data. And alternatively, you can move the history data from the real-time engine to the batch data warehouse as the data exceeds a particular time frame. Now, you do have to keep in mind that real-time analytics work on a particular time box. So it might be for the last 15 minutes or 1 hour of data that might be available to you for that real-time analytics. Now, if you want to work on the entire set of data or maybe a larger duration, say maybe for 6 months of data, you may still have to push it to the data warehouse where further refinements can happen. Then you can have a set of connectors, again, which will enable you to push data from the system to a database or maybe visualization tool to consume all those results. So this is at a very high level of what could be a big data strategy where you can actually mix both real-time and batch processing depending on your needs. And now, having shared our recommended strategy, it's now time to open up that floor for all your questions. And we've already actually received a few from the audience, and I just want to remind you that you can use the chat panel on the right to ask your questions. But before I take up those audience queries, I just want to quickly introduce Impetus Technologies. Impetus is a leading technology and R&D services provider with a really strong focus and established thought leadership in the area of large data analytics and high-performance computing. We really built top-tier expertise and offer consulting and professional services in technologies like Hadoop, numerous NoSQL DBs including Cassandra, MongoDB, Membase, and an entire range of commercial MPP products and ETL BI analytics tools. Our expertise spans the domains of large data management, cloud computing, data analytics, mobile, SaaS, testing, social media, web technologies, performance engineering, open source, among others. Okay, so it looks like it's time to get to those questions, and it looks like the first question that someone asks is, what are the differences between Storm and ESBs like Mule? Sarv, do you want to take that question?
Sure, Lisa. I think ESBs and real-time processing structures like Storm, they are infrastructures built for different systems. So while ESB allows you to communicate incongruent systems with each other, Storm is a framework designed to perform real-time computation. So when you have a system that you want to connect to another system that is both these systems are totally different and there is no communication channel between them, probably an ESB will solve this purpose. But a system like Storm is a perfect candidate where you need to process large amounts of data or maybe messages through a messaging queue.
Okay, Saurabh, I've got another question that someone would like to ask. And this one says, what is the advantage of Giraffe and Pregel over more common graph DBs like Neo or Infinite Graphs? What do you think?
Again, Pregel is in a very nascent stage at this point, but again, it is a project by Google. It is at a stage where Hadoop used to be years ago. So based on that paper which Google released, Hadoop came up. So similarly, based on the Pregel paper, we expect projects to come out. But Giraffe is very much real. It is a project by Yahoo, and the advantages that we can get from this kind of from Giraffe is actually it can leverage the Hadoop infrastructure. So this is the major advantage with Giraffe as against to other projects like Neo4j. And since it can leverage Hadoop, it can automatically adjust according to your Hadoop infrastructure. Giraffe itself is inspired from Pregel. So the biggest advantage that I can see is it can leverage the Hadoop ecosystem. Yeah.
Okay. Someone else would like a little clarification. They ask, you mentioned in one of the slides that you can use BSP for your supercomputing needs. They want to know, what is BSP?
Okay. So BSP stands for Bulk Synchronous and Parallel. So BSP is a computational model that is very similar to MR, and again BSP allows programmer to think in a parallel manner for a given problem, and you can compare it with MapReduce. So that's about it. So basically, if you have a system that's synchronous, you could use BSP to make it run parallelly.
Okay, thanks for that clarification. Well, that is all the time we have to answer questions live, but we got some other great questions from our audience, some which include, what are the differences between Cassandra and React, and why would you choose one over the other? What do you recommend for reporting on top of NoSQL databases? Someone else asked, can you comment on MPP database on SAN versus DAS? What is the limiting factor in analyzing all the data in real-time spaces? Is processing power, storage systems, DB systems, or maybe something else? Someone else wanted to know, is MongoDB a better solution for any of the scenarios discussed? And what architecture components would satisfy the desire to have an integrated NoSQL environment and be able to marry that data with both ad hoc defined user tables and events detected during unstructured data stream processing? So again, all those questions that were asked will be answered in a follow-up email to this webinar. Now, I'd just like to thank everybody in our audience for their time today, and we really hope that this discussion was a learning experience for everybody and will really add value to your big data initiatives. If you have any other questions, please feel free to email us at bigdata@impetus.com, or you can visit our website, bigdata.impetus.com. Once again, thank you so much for joining us in this session today. Have a great day.